Hello everyone. In this video, we will continue to consider topic 4.5 standing waves. In particular, we will consider observing, sketching, and interpreting standing wave patterns in strings and pipes, and solving problems involving the frequency of a harmonic, length of the standing wave, and the speed of the wave. In the last video, we began to consider standing waves in strings, and in particular, strings with two fixed boundaries. This is by far the most common type of standing wave in a string, um, and I gave a definition, or began to give a definition, of harmonics. The definition written was a little bit circular. I've adjusted it now, but it's still a working definition, and we'll refine it as we go along. For now, harmonics are the frequencies produced by the standing waves formed. So in this case, we can focus in on the different harmonics on a string. If you take a look at this diagram, you will see that in the first harmonic, the n equals 1 harmonic, you have two nodes, and that string connecting them sort of goes up and down. The entire length of the string bounces up and down like a jump rope. In the second harmonic, though, you increase the number of nodes and antinodes by 1. So in the second harmonic, you have 3 nodes and 2 antinodes. In that first harmonic, you had 2 nodes and only 1 antinode. In the third harmonic, you have 4 nodes and 3 antinodes. And this pattern continues. You should be comfortable sketching any harmonic, and in fact, in any standing wave problem you ever undertake, I strongly recommend that the very first thing you do, even if it's not asked for, is to sketch a diagram. To see why, what we're going to do is consider the relationship between the length of the string, the wavelength, and the frequency. And we're going to do so with reference to the diagrams. You always want to draw that diagram first. So, consider the first harmonic. Okay, this is also known as the fundamental frequency. It occurs at the fundamental frequency, and it involves the entire length of the string going up and down. You have 2 nodes and 1 antinode, as shown here. The 2 nodes on the end, the antinode in the middle. And the full length of the string is L, diagrammed here. Notice you only see half a wavelength. So if you sort of extended the image of this out, right, you would see sort of a full wavelength. But at any given time, you only see one bump, and it's either up or down. So you only see half that wavelength. Okay, now consider the relationship between L, the wavelength, and F. Well, given the diagram, you can see that if you only see half a wavelength, then lambda over 2 is equal to L. Given that, so we draw our diagram, we get lambda over 2 equals L. Given that, we can solve for the fundamental frequency. The fundamental frequency, F0, is equal to the velocity divided by the wavelength. Note, that's from the wave equation, okay, which we've used many times. And if the fundamental frequency is equal to the velocity divided by the wavelength, then it is also equal to v divided by 2L. And so we have a relationship between the frequency, the length of the string, and the velocity of the wave in the string. Notice this is not the velocity of sound. It is the velocity of the transverse wave in the string. We will see how these ideas connect to sound waves in a little while. So, this pattern can be extended, and not only that, we can discover patterns in the frequencies produced. So, this first harmonic is analyzed here in this first row. Consider then the second harmonic. In the second harmonic, we have 3 nodes, shown here, as well as 2 antinodes. You can see pretty straightforwardly that there is a full wavelength between the node on the left end and the node on the right end. So one wavelength is equal to L, the length of the string. If lambda is equal to L, then the frequency is equal to V over L. So this is actually an even more simple equation. Notice that this is equal to exactly 2 times the fundamental frequency. Um, one thing to note is that a sound with twice the frequency as another sound has a very distinctive flavor. We call that in music an octave. So if you have middle C and then the C an octave above that, that higher note C has exactly twice the frequency as the lower note. This idea in sound, usually when we're considering sound rather than the acoustic waves of these instruments, this is known as pitch. So pitch corresponds to frequency. All right, now consider the third harmonic. In the third harmonic, you have 4 nodes, 1, 2, 3, 4, and 3 antinodes. Okay, and here's where it gets a little bit tricky. Now, we're going to look at this diagram, and we need to figure out the relationship between the wavelength and the length of the string. So our question will always be, how many wavelengths fit in L? In the first harmonic, it was half a wavelength. In the second harmonic, it was exactly 1 full wavelength. And in the third harmonic, right, if we draw a wave, there's 1 wavelength, and then we get halfway through drawing another one, and we're done. So that means 3 halves lambda fit in L, or 1.5 wavelengths fit in the length of the string. So we write that relationship down, having drawn the diagram. That gives us that 3 lambda over 2 is equal to L. We can then solve for the frequency of the third harmonic. The frequency of the third harmonic is V divided by the wavelength, which should be equal to 2L over 3. So notice this says lambda here. That should say L. And actually, I'll fix it right now. So this should be 2L over 3. As a result, that formula is then equal to 3 times F naught, or 3 times the fundamental frequency. Notice a pattern here? Well, we'll see if that pattern continues. I would strongly recommend stopping the video right here and then attempting to draw and diagram for yourself the fourth and fifth harmonics and to derive the relationship between the fundamental frequency and those harmonics yourself. That is something you need to be able to do. In other words, you should draw the same kind of diagram for the fourth, fifth, and maybe even sixth harmonics. Try that out and then calculate the frequency based on your diagram. Then look at the next page.